Welcome to this chapter on graphing of the trigonometric functions, specifically to this first section on basic graphs. And graphing allows us to visualize the trig functions. We'll eventually graph all of the 6 trigonometric functions, but we specifically focus on the sine and cosine, and that's why whenever I refer to these here, I pretty much write y equals cosine or y equals sine. Eventually, in a few sections, I believe after the 5th section, we're going to graph y equals k plus a cosine bx plus c, respectively the sine. Where k is a vertical shift, used to be that for polynomials, that would be the y-intercept. That won't be the case here, but think of it as just that it shifts. But don't confuse it with a y-intercept itself. Sometimes it is, usually it's not. A is the amplitude. B is a coefficient that is linked to the period via b equals 2 pi over p, or p equals 2 pi over b. And c is a coefficient that is linked to the phase shift, where c equals negative b times the phase shift, or phase shift equals negative c over b. Those will come up in the next sections. For right now, we're just going to look at graphing the basic trigonometric functions. I already have them here, but I'm going to go over to the graphing calculator and show you how to do that. In the process, you may learn a couple of things about your own graphing calculator. So here we go. Okay, first of all, I'm going to put a list in of 9 numbers starting with 0. The reason I do that is because I would like to have a list that will give me multiples of pi over 4, but if you can't imagine that I try to type in here pi over 4, pi over 2, pi over 3, pi over 4, and so on, that would just take me too long. So that's why I use this list of just integers. I store these in list 1. So there we go, there they are. And now I'm going to do list 1 times pi over 4 and store that in list 2. There we go. And makes a kind of nice 0. There's pi over 4. There's pi over 2. There is 3 pi over 4. And there's pi, and so on. Okay, in the stat menu, it looks like this. There they are, again, those 2 lists. Actually, on second thought, I could have done L1 quicker by simply going to the stat menu and plugging them right in here. 0, enter, 1, enter, 2, enter, and so on. Okay, now I'm going to go to L3, and I'm going to see if I can do this here. L3 equals sine of L2. And there we get, nicely, the sine value for these. So here we have 0, and at pi over 4, of course, we come up with square root of 2 over 2. Then at 90 degrees, which is pi over 2, we have 1. And at 3/4 pi, we have, again, square root of 2 over 2. And at 180 degrees, we have 0. And then we get into the 3rd quadrant, so we start with the negatives. Okay, how do these look on the graph? Well, that's perhaps the second thing I can teach you here on the graphing calculator. Go to second stat plot. Go to plot 1. Turn it on. Use just graphing points, so don't try to connect them. Tell it what should be on the x-axis. Well, those would be the radians, which is list 2. Tell it what should be on the y-axis, that is the sine, which is L3. Oops. I need to do this here, so I get L3. There we go. And then the mark, I prefer these little squares here, so this will be fine. Then I go to graph, but unfortunately it's going to look a little bit like this here. What I'm going to do instead is I'm going to change the window setting. I may want to start at 0, because that's where I went to, and perhaps go to 2 pi for the max. And for the scale here, maybe pi over 6. And then for the minimum and maximum values for the y-axis, -2 to 2, and then I graph, and there it is. So here the sine, as we know, starts at 0 here, reaches its peak at pi over 2, comes back to 0 at 180 degrees, goes into the negative in the third and fourth quadrant. We're hitting -1 at 270 degrees, or 3/2 pi, and then going up to 0 again when we get to 360 degrees. Okay, let's do the cosine. Will look really similar. The procedure. I'm going to go over here 1, and then I'm going to say L4 equals the cosine of L2 is, parentheses, enter, there we go, so there it is. Go to second dot plot, and switch the L3 to the L4, because that's where we have the cosine sitting now. And in contrast, of course, this is what we're going to get for the cosine. It looks kind of similar, but it starts at 1, and we knew that cosine of 0 is 1. Goes down to 0 at 90 degrees, or pi over 2, reaches -1 at 180 degrees, goes back up to 0, and then back up to +1 when it comes back to 360 degrees. Okay, I'm going to do one more graph, which is going to be the tangent. So I'm going to go over here, L5, and I'm going to put in tangent of L2. And now something interesting will happen. At least I expect it to happen, that we get an error. Why? What happened? It says something about domain. Well, what happens here is that, let me erase this for now, that as we're trying to take the tangent of list L2, here's list L2. There it is. Tangent of 0 is fine. It's going to come out to 0. Tangent of pi over 4, or 45 degrees, is going to be fine as well, because it's going to be 1. But here, tangent of pi over 2, or 90 degrees, we know is going to be infinity. So we're basically telling the calculator, calculate infinity for us, which, as we know, whenever we tell a calculator to do that, it will give us an error message. So I have to do a little trick here. Instead of doing L2 equals multiples of pi over 4, I have to avoid those multiples of pi over 4. So, for example, what I could here do is take L1 times 0.2 maybe. There we go. And now I go over to list L5 and say, hey, tangent of L2. And because I avoid these multiples of pi over 4, that's why I don't get into trouble. And this one here I have to change to L5. And then graph. And there is the tangent, at least part of it. Presently, I mean, it should start here again, but I think I need more values for that. But basically, it's going to go towards infinity right there. Okay, with that one, I'm going to go back to the Word document. And here you see the same 3 graphs: sine, cosine, and tangent. Apparently, in preparation for this, I must have prepared that the tangent, a few more points prepared that I left out in the graphing here, but you basically see what I wanted to accomplish here. I should point out here, note that the sine and the cosine kind of look similar, especially if you graph more periods than just the one that I did here. And then, in fact, sine equals x plus pi over 2 is the same as cosine x, and cosine x minus pi over 2 is the same as sine x. That's an identity that you that is called a cofunction theorem, and you will find it in several places in our textbook. Okay, let's go over here to a summary of the graphs of the basic trigonometric functions. For sine x as well as cosine x, the domain are all real numbers. You can plug in any number you want. You will always come up with a nice result. The range, and this depends on the amplitude. When the amplitude is 1, the range would be -1 to +1. Of course, when the amplitude is 3, well, it's going to be negative 3 to 3, or if you have a vertical translation, then it might be pushed down, but you're confined to a range. That means you have like a horizontal band going across your horizontal band going across that. It doesn't exceed above or below. A period, if the coefficient b equals 1, would come out to 2 pi. That means every 2 pi it repeats. If the period is something else, as we will find out in the next section, then we, of course, get a different kind of period. Okay. The tangent is defined for all x with the exception, for all x element of the real numbers, with the exceptions of 90 degrees, of course, as well as adding any kind of multiple of pi. So 90 degrees and 270 degrees, 450 degrees, was it 630 degrees, 650 degrees, I believe. I don't know there. Maybe 630 degrees, I believe. And so on. And that's what we see here. The tangent hits infinity and negative infinity, so it can't be defined there. The range is going to be all real numbers. Notice that it goes up and up and up, and then comes from very below. There we go. Amplitude is cannot really be defined for these ones here. A period, it has a coefficient a, but really not an amplitude. What happens to these tangents and the other graphs is that they might become a little bit wider. It's especially nice to see for secant and cosecant, where they're becoming, and by the way, I'm towards the very bottom of my Microsoft Word screen here. You want to scroll down. That right now it looks parabola shaped, but if you increase the amplitude, then it might become more trough shaped. Okay, the period, as you can see, is pi, and you notice it repeats itself faster than what the sine and the cosine do. It's really similar for the cotangent, and of course the cotangent is not defined where the tangent hits 0, because then we would have 1 over 0. So the cotangent would not be defined at 0 degrees, 180 degrees, 360 degrees, 540 degrees, and so on. The range also is all real numbers. Again, really not an amplitude, and it repeats also every pi. The secant and the cosecant, I'm going to scroll this down now a little bit. As we can see, they're also x element of all real numbers, with those exceptions. Whenever the cosine hits 0, that's where the secant is not going to be defined, and whenever the sine hits 0, that's where the cosecant is not defined. That's why you have these exceptions. The cosecant is not defined at 0, 180 degrees, 360 degrees, and so on. You can see the range. Since the sine and the cosine have a range between -1 and 1, that means the inverses of them have to have a range of y either being less than -1 or more than +1, respectively, greater or equal to +1, smaller or equal to -1. Again, not really an amplitude there, and it repeats just like the sine and the cosine every 2 pi. I'm going to go over to the graphing calculator, and we'll graph each one of these. You already saw them, but let me show you how to graph them in real time. I have to turn the stat plot off that I had turned on earlier. Okay, it's sufficient. And then let's see, for my window here, maybe I want to have 3 pi or 4 pi. I think I used 1, 2. It's not like 3 pi maybe. Let's go there. For that margin, I'll leave it at -2. And now I'm going to go to y equals and type in sine x and graph. And there's the sine curve. There we go. And then I go and I do cosine of x. And it looks really similar, except it starts at 1 instead of 0. And then I'm going to do the tangent. And of course, it shoots to infinity, comes from negative infinity, goes to positive infinity, repeats itself every 180 degrees, rather than the 360 degrees for the others. And then I'm going to go ahead with the inverses, and notice that on the graphing calculator we don't have inverses up front. They may be in the catalog. I always just use, well, them as inverses. So I'm going to do second insert 1 over, or I could have said tangent to negative 1. That would have worked as well. This one we know is now the cotangent, and of course it looks kind of similar to the tangent but kind of flipped. Again, it repeats itself every 180 degrees. The cosecant, the secant is going to look as follows: 1 over cosine. There we go. Starts at 1 and then goes all the way up, and you have these troughs towards the top, and it repeats itself, and the troughs towards the bottom. It repeats itself every 360 degrees, and the cosecant looks really similar to that, just starts in a different place. So there we go. That's how we basically graph them. I have a couple little addendums to this lecture. So here, this is what we just did. We just graphed them all. So most of the time we'll be looking at the sine and cosine graphs, and therefore the other trigonometric functions, tangent, cotangent, secant, and cosecant, while they show up once in a while, actually have their separate section. Okay, one more little thing, and that is even and odd functions, which are in this chapter. Eventually it will become important to determine trig functions of negative arguments, and there it's kind of important to understand what an even and an odd function is, because it makes us calculate it faster. Cosine theta is an even function, because if you plug in a negative number right here, it comes out to be the same cosine as if you just used the positive number. That's because this one here is in quadrant 4, and this one here ends up in quadrant 1 if we use angles between 0 and 90 degrees. So cosine of negative 30 degrees, and we know that, is going to be the same as the cosine of 30 degrees, which is the square root of 3 over 2, so 0.866 for both of them, and again, it's positive as well, positive result as well. So cosine of 30 degrees is the same as cosine of negative 30 degrees, and that's the that is the definition of an even function, that it doesn't matter if you plug in a negative or a positive argument for the x or the theta in this case. Y equals x squared, the parabola, for example, is an even function. Sine theta is an odd function. That means it does depend on if you have a negative or positive theta, but what happens then is that that negative is pulled towards the front. So, for example, sine of 45 degrees, we know, is the square root of 2 over 2, 0.707. Sine of negative 45 degrees is also 0.707, but with a negative in the front of it, because we're in the fourth quadrant, so negative 0.707, points down. And in order to make this equal to the original angle, we say that sine negative 45 degrees equals negative sine 45 degrees, so the negative pulls towards the front, and that's where we have a negative in front of the result as well. I tried to highlight this here just nicely. There it is. Okay, as I said, this becomes important when we look at trig functions with negative arguments. And with that, I'm going to conclude this section on basic graphs.